Hello and welcome to the Axon Instruments webinar series. My name is Jeff Weber and I'm the product manager for electrophysiology at Molecular Devices. I'm very excited today to introduce Dr. Jin Yan from Molecular Devices. Dr. Yan will be highlighting using clamp fit in pCLAMP to perform trace combinations, rise and decay calculations, and curve fitting. Then we will open up the floor for questions and answers. Before we begin, I want to give you a quick introduction on how to ask questions. At any time during the talk, you can ask questions by clicking on the Q&A window and selecting Send to Panelists. Type in your question and click Send. Keep in mind that we do try to get to as many questions as we can, but there's not always time to get to every question. We will follow up with an email if we don't have the opportunity to discuss your question live. And now let me jump in with an introduction to our speaker, Dr. Jin Yan. Dr. Yan is a technical support application scientist. Dr. Yan joined Molecular Devices in 2015 and brings over 10 years of experience using Axon instruments. She's been heavily involved with current development of pCLAMP software. Dr. Yan received her PhD degree in medical pharmacology from the University of Arizona and completed her postdoc training at University of Washington. Her research interests include molecular mechanisms of migraine and presynaptic modulation of calcium currents by calcium sensor protein. Dr. Yan joined Molecular Devices in 2015. And now I turn it over to Dr. Yan.
Hello, everyone. Thank you for attending the webinar. And thanks, Jeff, for the introduction. I've been with Molecular Devices for a year and a half and talked and emailed with a lot of our users. I noticed that there are several issues that have been raised a lot, and I would like to take this opportunity to discuss these functions with you. As you can see from our title, today we are going to cover three main topics: combine traces, calculate decay and rise time constant, and fit curves. So today we are going to use clamp fit. Clamp fit is the analysis module of pCLAMP software. With hardware and software, Molecular Devices provides an overall solution for electrophysiology studying. clamp software works with our hardware, amplifier, and digitizer to acquire data. The acquired data then will be analyzed by clamp fit software. So here is how clamp fit software looks like. Once you open the clamp fit, you will see several windows. The traces recorded in the clamp is open in the main window, and the result window presents the analysis results. The lab book window keeps records of everything that has been done in the clamp fit software. So now we are going to proceed to our topic today. First, we are going to talk about how to combine traces. This function is very important for data illustration. Here are some examples. For drug discovery studying, most likely you will have to make a figure that shows the effect before and after the drug application. The first two graphs shows the control traces in black, and the red trace is the trace after drug application. So that shows how your drug works. It blocks this current. So the bottom figure shows the real base current. So the black trace is before the current injection reaching the threshold for action potential firing. And the red trace is when you reach the threshold for action potential firing. So most likely you will use this function to lay out your data for presentation. There are different ways to achieve this function. So today we are going to talk about two methods. First, we are going to use the Concatenate Files function. In order to use this function, these traces need to be made with the same sampling rate, and they need to be at the same length. So if you are uncertain how you recorded these traces, you can take a look at the properties of the traces by going to the file properties. So as you can see, this is an example. So for this file, it has been sampled at sampling rate of 10 kHz. The interval is 100 milliseconds, and then the trail length, it has 2 sweeps. For each sweep, it's 500 milliseconds. So there is a lot of information in this window, and I can show you when we are doing the live demo. So here's where you can find the Concatenate Files function. It is located in Analysis Concatenate Files. So now let's take a look at the demo. So I'm using CLAMP fit 10.6. So this is how my CLAMP fit looks like. So first, I'm going to open my 2 traces. You can open it either by file open, or you can just drag and release them into the CLAMP fit software. And you can lay out your window by press this key. So let me show you how my trace looks like. So this is my first file, and there are 2 traces. And this is my second file. Again, there are 2 traces. So let's look at the properties of file 1 first. So I'm going to highlight the file 1 and go to File, Properties. So this file is recorded at sampling rate of 10 kHz, and it has 2 sweeps. Each sweep is 500 milliseconds long. And if we scroll down, we can see the protocol that we recorded this file with. So the first trace, we injected 20 pCLAMP current, and the second trace, since the delta is 10 pCLAMP, we recorded by injecting 30 pCLAMP current. So now let's take a look at the property of file 2. So again, highlight the file 2, go to File, Properties. So it is similar. It is sampled at 10 kHz sampling rate, and it has 2 sweeps. Each sweep is 500 milliseconds. And close that. In order to combine these 2 traces, I will go to the Analysis, Concatenate Files, and select all the files, and click OK. You can see a new window pops out with the trace combined together. So this is very fast and straightforward. However, one disadvantage of this method is that it won't allow you to choose which trace do you want to combine. For example, you have a file with 1,000 traces, and you only want to illustrate one of them. So how would you be able to do that? So next, we are going to introduce another method. So transfer traces. Transfer traces is a very useful tool. It allows you to convert your Axon binary file to Axon text file. It is not only useful for combining traces, also it is useful in converting data and allow the same data to be analyzed by third-party software. The default file format that CLAMP recorded is Axon binary file. By using transfer traces, you can change it to Axon text files. So basically, it transfers your trace to text and lay the data out in a spreadsheet. For each data point, there will be a corresponding value linked with it. once I do the demo, it will be more clear. The function can be found at editor transfer traces. So it's here, editor transfer traces. So now I'm going to do a demo for combining the first file and the second trace of the second file. So to do this, we need to bring out the results window. So the results window is here. I'm going to lay out it again. So I'm going to transfer traces for the first file first. So I'm going to highlight the first file and go to Editor, Transfer Traces. So here you can choose which region to transfer, and also you can choose which trace to transfer. So for us, right now we only have one signal, so we can choose the all visible signals. And we have two traces, so I'm going to transfer both of them. So I'll click OK. And I'm going to transfer the whole trace from the beginning to the end. So once I click OK, now you can see the data points at each time point. So I'm sampling in 10K hertz. So you can see each 0.1 milliseconds, there will be one data point. So the time column is spaced every 0.1 milliseconds. For each data point, there are two corresponding y-axis number. So that's your trace 1 and trace 2. So now I'm going to transfer all the traces with a second file. So I'm going to highlight file 2 and then go to Editor, Transfer Traces. Again, I'm going to transfer the whole region and transfer all traces. So I'm going to click OK. So as you can see in the spreadsheet, now you get 3 more columns. Since the sampling rates are the same for the two traces, you can see the time column is the same. So it's spaced at each 0.1 milliseconds. So we can delete one of them. So I'm going to delete the time column for the file 2. And now you can choose which trace you want to combine. For example, I only want to keep 3 traces instead of 4. So I'm going to delete the trace 1 for the second file. Delete this. So now you have your 3 traces. So for this result, you can save it. Now you want to save it as Axon text file. I'm going to call it combined. Save it. So now let's open this file and see how it looks like. So I'm going to go to File, Open Data. You need to change the file type to Axon text file to see this file. So now we are going to open this one. So as you can see, instead of 4 traces, now we have 3 traces in this combined data file. So the other thing nice about the ATF file is it allows you to open it with the third-party software. For example, we can open it with Excel. So let me show you that. So I can go to File, Open. So again, in order to see this file, you need to change the file extension here to all files. So now you can see the ATF file. So once you click Open, this text import wizard will pop out. The default setting is fine, so you can just click Finish, and you should see your raw data. And this file can be used by MATLAB or other softwares for further analysis. So So the next issue is, what if you have files with different sweep lengths? Will you still be able to combine some? So the answer is yes. So I'm going to show you another demo. So as you can see, here I have two files. The first file, the file 1, I have recorded for 600 milliseconds. And for the second file, the file 2, I have recorded for 1 second. But you can see our protocol is set between 100 milliseconds to 500 milliseconds. So can I combine the 100 milliseconds to 500 milliseconds of file 1 with 100 milliseconds to 500 milliseconds of file 2? The answer is yes. So in order to do this, we need to set the cursor first. So we want to set the cursor 1 at 100 milliseconds and cursor 2 at the 500 milliseconds. By double-click the cursor, you can set where it is. So let's click the cursor 1 first for file 1. So here, I'm going to set it at 100 milliseconds and click OK. And for cursor 2, I'm going to set it at 500 milliseconds and click OK. So now I can use the editor transfer traces. So instead of transfer the full trace, this time we are going to transfer a region, the region between the cursor 1 and cursor 2. So I'm going to click OK. So you can see the time column is from 100 milliseconds to 500 milliseconds. So now we are going to do the same thing for the file 2. So cursor 1 at 0.1 second, that's 100 milliseconds. And cursor 2 at 0.5 seconds. And again, I'm going to use the transfer trace function to transfer the region between cursor 1 and cursor 2 of file 2. And click OK. So you can see, again, 500 milliseconds is being transferred. So I'm going to delete the time column for the second file, since it's the same as the first file. And I can save this result. So you need to save it as an ATF file. Now we can open this new file. And as you can see, we have our 4 traces. That's the trace originally from 100 milliseconds to 500 milliseconds. So by using this function, you can combine any part of the trace that you are interested. So now we are going to talk about our second topic, tau calculation. One frequent asked question I get is how to calculate inactivation time constant tau. So today we are going to talk about the tau calculation. In electrophysiology, tau is a very important measurement to reflect the activation kinetics and the inactivation kinetics. In order to calculate tau, we first need to understand what is tau. So here is the definition of tau. For systems that increases in value, tau refers to the time required to reach 22.8% of the final value. For a system that decreases in value, tau is the time it takes for voltage to fall to 36.8% of the initial value, the peak value. So there are different ways to calculate the tau. So today we are going to use statistics function and the curve fitting function to find out the value for tau. So now let's move on to the demo. So this is a nice looking sodium channel current. It's a current with negative going peak. It has two phases, the rising phase and the decay phase. Since it's a negative going peak, so the first part, this part is the rising phase, and the second part, this part, is the decay phase. So for the rising part, we can calculate the rise time constant, and for the decay part, we can calculate the decay time constant. So what we want to do is, first we want to put the cursor 1 and cursor 2 at the baseline region. And we want to put the cursor 3 and cursor 4 to cover the peak of this current. So now let's go to the analysis statistics. So first, the peak polarity is negative going peak. And the mean value is the value between cursor 1 and cursor 2. And our search region will be between cursor 3 and cursor 4. So we are going to calculate the rise time and decay time. So based on the definition of tau, so the base time will be, the rise time constant will be the rise time from minimum 0% to 63% of the maximum. And the decay time constant will be the decay time from maximum 100% to the minimum 37% of the maximum. So now we are going to click OK. And in your result sheet, you should be able to find your rise time and your decay time. So this is your rise time constant. That's 0.136 milliseconds. And the decay time is 0.91 milliseconds. This method is simple and straightforward. However, this is not the most elaborate way to calculate the time constant, as we know that under most conditions, the channel kinetics can be complicated. It is not always as simple as one inactivation component. For sodium channel at certain voltage holding level, there will be fast inactivation and a slow inactivation. So how can we differentiate them? So next, we are going to use the curve fitting function to calculate tau. So we are going to fit the rise phase and decay phase respectively to exponential function and figure out what's the tau for the rise phase and decay phase. The fit function fits the curve between cursor 1 and cursor 2. So I will do the rise phase first and put the cursor 1 at the beginning of the rise phase, and the cursor 2 at the peak of the current. So for the statistics function, as we can see that everything is compared with the baseline level and the peak level. However, the tau fitting function, it doesn't specify the baseline level and the peak level. So that means the tau value will change depending on where you put the cursor. So you should be very careful about where you put the cursor. It needs to be right at the beginning of the curve at the baseline, and the second cursor needs to be right at the peak position. So the fitting function is located at analysis fit. So we are going to use the exponential standard fitting function to fit this curve. The number of turns here reflects how many different kinetic components is involved here, and we are not sure about that. The nice thing about CLAMP is that it comes with the compare function. So you can find it in data option tab. So there's the compare model function. So it will automatically compare 110 to 610 and find out the best fit for you. So now let's run it. You can see the blue line fits nicely with the original data. And if we go to the analysis fitting result, you can see the best model that the CLAMP has found is a 110 fitting model, and the confidence interval is 0.95. And if we go to the parameter, we can see the tau calculated is 0.154 milliseconds. It's very close to what we have calculated in statistics function, that's 0.136 milliseconds. Now we can continue and try to do the decay time constant. So again, it is very important where you put the cursor. So the first cursor needs to be right at the peak. And the second cursor needs to be when the trace goes back to the baseline. And again, we are going to use the compare model function to see which one is the best fit. And we are going to use the predefined standard exponential function to fit this curve. And click OK. So okay, so let me try put the cursor again. So let's go to the fitting result. So again, we can see the best number is 110 fitting, and the confidence interval is 0.95. And in the parameter, we can figure out the tau is 0.96 milliseconds. Again, it's very similar to what we have found in the statistics function, and that's 0.19 milliseconds. So next, I'm going to show you another example. So this is a trace that looks very different from the first one. As you look at the time scale, you can see that it has the fast inactivation component. However, it takes really long to go back to the baseline. So it indicates the existence of the slow inactivation component. So let's try fit with the exponential fitting function and see how many different components it has. So I'm going to put the cursor one at the peak. And I'm going to put the cursor at where it went back to the baseline. I'm going to use the exponential standard fitting and use the compare model function. So as you can see, the best number of turns that fits with this trace is 2 turns. So that means it has the fasting activation and also the slowing activation. And also, it calculates two taus for us. The first tau is 6.5 milliseconds. So that's the tau for the fasting activation. And the second tau is 27 milliseconds. So that's the tau for the slowing activation. So overall, I would say fitting is a more elaborate and accurate way to help you analyze your current. It tells you how many different inactivation components is in your trace. So next, we are going to move to our next topic, fit and plot and fit the current voltage curve. So most frequent used function for electrophysiologists is the IV plot function. Today, I'm going to demonstrate how to plot the current voltage curve and how you can fit this curve and get the reversal potential. So most of our users are probably very familiar with how to plot the current voltage curve. So I'm going to demo it fast. So here is a nice looking sodium channel trace. The first thing we want to look at is, so here there is about 40 pCLAMP lead current. And before we do the IV plot, we want to get rid of this lead current. So we are going to put cursor 1, cursor 2 here. And we are going to go to analysis, adjust, baseline. So for this curve, the leak is very consistent. It starts from the beginning of the trace to the end of the trace, and it doesn't change the amplitude. So we can use the subtract mean function. We are going to subtract the mean between the cursor 1 and cursor 2. That should bring the trace back to 0. So once I click OK, you can see that now we get rid of the lead current. So now let's set up the cursor to do the IV plot. So we still need a baseline here. And for cursor 3 and cursor 4, we want it to cover the peak here. So here is our shortcut to plot the IV plot. So now we click this. For x-axis, we want it to be the holding voltage. So for this trace, we have 3 epochs for each sweep. Epoch 1 is the baseline holding level, and epoch 2 is the test pulse level. It has 10 millivolts increase for each sweep, and epoch C is the baseline holding level again. So when we plot the trace, we need the pulse level at the test level, so that is the epoch B level. For the y-axis, we want the peak here. We want the peak level here. So the peak is negative going, and the region that we want is between cursor 3 and cursor 4. So now let's click OK. We can see our nice looking IV plot. The sodium channel current voltage plot can be fitted with this equation. The equation looks very complicated, but let me break it down and explain it to you. The variable in this equation is the test pulse, so that's the V. And apart from that, there are 4 parameters in this equation. The first one is G. So G is a factor reflecting the number of active channels. And there's the VR. VR is the reversal potential. And there is the Z. Z is the apparent gating charge. So gating charge is the movement of charged voltage sensor effector built in the voltage-gated ion channel. As the voltage sensor moves, they generate small transient gating current that flows as channel open and close. So it's a very important kinetic for voltage-gated ion channel. Here, Z is the apparent gating charge. It's not the accurate actual gating charge, but it is proportional to what the actual gating charge is. So the fourth parameter is V half. So it's the half maximum activation potential. By fitting the IV plot, you can get an estimate of what the apparent gating charge is. And also, if you have an IV plot that looks like this, you will be able to estimate what the reversal potential will be. So here I'm going to do a demo on how to fit this curve. So instead of using the predefined function, we are going to use the custom function this time because it's a formula that does not exist in the predefined function. So here are some instructions about how to write formulas. So the independent variable, which we have here is V, need to be expressed as x, x1, x2, x3, etc. And the parameters must be expressed as P1, P2, P3, etc. So we have 4 parameters. So we have P1, P2, P3, and P4. So based on this instruction, we can put our formula like this. That is our original formula. I just replaced our parameter with P1, P2, P3, and P4. And also, I replaced the variable with x1. So different from the predefined function, for customer function, you need to put the seed value by yourself. Otherwise, the CAMFit won't know how to fit this formula. So the seed value is put here in the seed value tab. So we have 4 parameters, so we need to put the seed value for these 4 parameters, P1 through P4. So P1, G refers to the number of active channels. So one thing I have to mention is this seed value does not need to be accurate, but it has to be a reasonable value that has some meaning. So for the P1, G reflects the number of active channels. So we can estimate this number. So as we can see, for this channel, the peak current is about 800 picoamp. So we can divide the peak current by single channel current for sodium channel, which will be about 4 picoamp, and the capacitance. So a normal cell capacitance is about 20 picofarad. So here we can calculate the G about 800 picoamp divided by 4 picoamp and divided by 20 picofarad. So the number is around 10. So we are going to put 10 for P1. And for the reversal potential, we can see here it's about 50. So P3 is the apparent gating charge. So for sodium channel, a lot of previous study has studied that the gating charge for sodium channel is from 6 to 10, depending on the subtypes. So here we're going to put the average value 8 here. For the V half, we can see from our IV plot, it's about minus 10 millivolts. So now we click OK. So we can see our fitting curve that lay out nicely with our original IV plot. So in our result window, we can see that now it gives us the actual P1, P2, P3, P4 value based on the fitting curve. So we can see the G value is about 18, and the reversal potential is about 52 millivolts, and the apparent gating charge is about 4.44, and the V half is about minus 10 millivolts. So these numbers are important channel kinetics, and you can compare these numbers between different groups. So that is all for today's topic. Hope I have provided some useful information here. Now we are going to take questions.